way that the schedule is set up. We conclude on a Wednesday, and so I think the only change is for the Wednesday is physiology. Okay, it's been about a week since we talked about the physiology of the heart. Recall that we discussed two general families of cells. This is a dramatic oversimplification, but there are two general families of cells. We talked about conduction cells and we talked about contractile cells. Now, within that large category of conduction cells, we specifically focused on pacemaker cells in the pacemaker node or the sinoatrial node of the heart, which is up there in the posterior region of the right atrium. And so we're going to begin with a discussion of that today, but just by way of reminder, recall that the SA node normally is the clock. It's the timekeeper, it's the pacemaker that establishes the general rhythm of contractile cell activity. Now, there are some exceptions to that. We need to talk a little bit about how the heart functions as a functional syncytium. We don't say that it's a true syncytium. We don't have multinucleate cells as we did in skeletal muscle, but we have a functional syncytium to the extent that, recall, the contractile cells of the heart, the cells that make up the myocardium in both the atria and the ventricles, have extensive gap junctions embedded within those intercalated discs. Consequently, when one contractile cell depolarizes, adjacent cells depolarize. So with that brief overview, let's talk about the conduction pathway of the heart. Now, in the illustration that you see here, we can see the SA node right up here in the right atrium. Remember that normally will be the fundamental timekeeper or clock. It's going to, on its own, generate a rhythm that will then be propagated through these purple structures that you see here. These purple structures represent the conductive pathways. And so the signal, more or less, is going to be propagated in this direction down to this structure called the AV node, and to the AV bundle or bundle of His here, and then into the branch bundles, and then in what we call the Purkinje fibers. But in general, the signal is going to be propagated in this direction and then up in the walls of the myocardium. Now, the only other pathway that isn't shown here is that as that SA node sends its signals, and you've got to keep in mind it's conveying signals not only to these conductive cells and the purple pathways here, but it's also exciting the myocardium of the atrium here. All right, so there's going to be that functional syncytial depolarization of the atrial myocardium. But the pathway that's not shown here is, of course, there are also internodal pathways to the left atrium, which you don't see here. We'll just call those interatrial bundles, sometimes called Bachman's bundle or whatever. But the signal is being propagated over to the other side as well. So the illustration here is simply showing you that in addition to this, the point I just made, that in addition to excitation of the internodal pathways to the AV node, there is also excitation of atrial myocardium, so it's going to begin depolarizing. We've already established that the myocardial cells, again, this is the SA node here. These have those special pacemaker potentials and action potentials that are then propagated to the adjacent myocardial cells, and then by virtue of the intercalated discs, we have communication or propagation of that depolarization throughout the atrium. And it can only go so far for reasons we'll talk about in just a moment. So do be aware of what we mean by autorhythmic cells. These autorhythmic cells are the cells that have that pacemaker potential. Now, we do have a bit of a conundrum here because remember, there was a reason that I showed you those cells in a petri dish earlier. Remember the cells in the petri dish, and they have so all of the cells of the heart are, in theory, autocontractile. They have the ability to contract on their own at their own native rhythm. It's just as the general rule will be that the heart as a unit, as a functional syncytium, will contract at the highest rate or the highest frequency of signal that it receives. All right, so the highest signal will determine usually the frequency of conduction, or I'm sorry, the frequency of contraction. And that being true, it is normally the SA node that has the highest frequency of highest signal frequency, the highest, the greatest number of excitations or action potentials per unit time. We'll work through some more of that as we go. All right, so the next few illustrations, I just want you to pay attention to not only the pathway, but also the time involved in these signals arriving or leaving one point and then proceeding to another. So we're up here at the SA node, and we can see the signal then being propagated via the internodal pathways to the AV node. Now, that propagation takes about 50 milliseconds, and I do want you to be familiar with that approximate time interval. It's going to be affected by a variety of factors we'll talk about later. So roughly 50 milliseconds for the signal to be propagated down to that AV node. At that point, the signal is at the AV node, and the signal is going to be slowed. The signal at this point is going to be delayed, as if the electrical signal has to be delayed, and the reason for that primarily is to allow time for the ventricles to fill with blood. So the general idea here is it took about 50 milliseconds for the signal to pass from the white circle there to the dark purple circle there. And then it's going to take another 1/10 of a second before the signal leaves the AV node, then to pass into this region right here called the AV bundle, or the bundle of hits. So in effect, the AV node and its surrounding area is delaying the signal about a 1/10 of a second. So that when all is said and done, about 150 milliseconds have elapsed, 50 plus the 100 milliseconds of the delay. Now, this ability of the AV node to delay the signal is fairly important for the reason we just talked about. It's one of the safety mechanisms that allow for ventricular filling. If the SA node is sending a signal that is much too rapid, you can see here at very, very high rates, let's say in the order of a couple hundred signals per minute, the AV node will shut down completely. That's called decremental conduction. It begins to slow, and of course that's a safety measure as well, because what would be the problem in a heart that has a functional syncytium is contracting too rapidly? What would be the real problem there?
Fibrillation?
I'm sorry?
Atrial fibrillation.
Well, that would be atrial, but before we get into all the details of those ideas, just in general, you have a pump. And of course, a pump, if you've ever played around with, I don't know, a pump to fill your lawnmower or whatever, they have these little peristaltic pumps. What's the problem if you start contracting that manual pump too rapidly? Yeah, it doesn't fill up sufficiently. So each consecutive stroke yields a lesser volume. So the problem with very rapid conduction, as we'll see later, very rapid conduction and contraction, is that the heart is beating frantically, but there isn't much blood that's leaving the ventricles because there's insufficient time for the blood to enter and fill the ventricles. So, yeah.
So the AV node conduction will actually slow more with a faster rate.
We need to talk more about this later. Yes, as the rates get very high, it'll shut down altogether.
So when you say shut down,
it just will stop conducting the signal.
okay.
At which point, well, we'll come back to that later. Then the signal passes very rapidly. What they really don't show is this signal passing through the annulus fibrosus here, that little region right in here. But you'll notice the signal passing into the branch fibers is very, very rapid and only takes about 25 milliseconds. Very, very rapid. So at this point, at the time we get the signal approximately down to the apex of the heart, we're talking about 175, 200 milliseconds at most. In general, the signal propagates a little more rapidly on the left side. That's one of the reasons that in reality, although we won't worry about this too much, the left side contracts a little bit before the right side. The left ventricle contracts a little bit earlier than the right ventricle. By the way, getting back to the conduction, a lot of this is dependent upon the relative abundance of gap junctions in these electrical conduction, in these pathways. And at the AV node, there's a relative paucity. There's a reduction in the number of gap junctions. As by the time you get into this area, the density of gap junctions increases dramatically, and that's in part responsible for the increased speed of conduction. And then finally, you can see there's propagation of the signal from the interventricular septum here, those bundle fibers, into the walls of the myocardium, and that's achieved by the Purkinje fibers, have a very distinct histological appearance. And so by the time the signal then has initiated or originated in the SA node and then has made its way up the walls of the myocardium, well, you're talking close to a quarter of a second, 250 milliseconds or so, something along those lines.
Number of gap junction starts here.
There are three words we'll come back to later, but these are words you should know. They're going to turn up in the clinical literature, although they're not always uniformly observed. So a chronotropic medication or therapy or effect alters the heart rate. Chronotropic refers to changes in the heart rate.
Okay, like that.
Inotropy, probably the other one that's more that you'll see with even more frequency, refers to the contractility, the force of contraction. We talked about a number of factors. And then the last one here, the last one there is dromotropic. Dromotropic effects refer to the speed of conduction from the SA node to the AV node to the bundle of His and so on. So anything that alters the speed of conduction is going to have a dromotropic effect. Logically, in most cases, dromotropic effects will have also chronotropic effects, but there are a few cases, a few medications you will have at your disposal where that doesn't happen. So as we talk more and more about cardiac function, we need to draw upon our basic understanding of physical relationships and physical principles. I've talked about frequency, the number of times, the number over time, I guess is the best way to think about this. So don't confuse that with velocity. Velocity is the distance over time. So if you look at the little table here, we have the numbers on the right side of our illustration that more or less correspond to what we just talked about. These are the numbers in milliseconds for the signal to pass from one point to another. You'll see different numbers and different sources. You get the idea. Generally, a fifth or a quarter of a second for that signal to pass to the walls of the myocardium. But notice on the left we have a table of conduction velocity, again, distance over time. Now, as you look at this table, tell me, reading that table, where is conduction speed the greatest in that pathway? Where is conduction speed greatest? All right, so good. Make sure you don't misinterpret these numbers. These numbers are not time, these are velocities, so exactly right. And we made that point before. Here we're talking about meters per second. So most rapid, and you can see the conduction velocity in the atria and the ventricles is roughly comparable. Where is it slowest? Be sure you pay attention in the AV node.
Action potentials originate in the sinoatrial node and travel across the wall of the atrium from the sinoatrial node to the atrioventricular node. Action potentials pass slowly through the atrioventricular node to give the atria time to contract. They then pass rapidly along the atrioventricular bundle, which extends from the atrioventricular node through the fibrous skeleton into the interventricular septum. The atrioventricular bundle divides into right and left bundle branches, and action potentials descend rapidly to the apex of each ventricle along the bundle branches. Action potentials are carried by the Purkinje fibers from the bundle branches to the ventricular walls. The rapid conduction from the atrioventricular bundle to the ends of the Purkinje fibers allows the ventricular muscle cells to contract in unison, providing a strong contraction.
And of course, in those successive contractions, we're looking at something called the cardiac cycle. We'll turn our attention to momentarily. But the cardiac cycle, the rhythmicity of contraction, is entirely dependent under normal circumstances upon that conduction pathway we just talked about. Here I did it again. All right, so the SA node, which we've indicated is the normal timekeeper, the normal clock of the heart, will have its own autorhythmicity, its own excitation rate that is typically on the order of 100 excitations or 100 action potentials per minute. So keep that in mind. The SA node, left to its own devices, would generate something along 80 to 100 action potentials per minute. What is your heart rate now? What is your resting heart rate? Is it, most of you have 80 to 100? Yeah, I'm so excited to see you each day. Mine usually is, but for most of you, it's going to be considerably lower. Why is that? So this is we've indicated here. You see the fundamental problem. The SA node is the timekeeper, the rhythm keeper, the drummer of the heart. Left to its own devices, it will cause the heart to contract at around, let's say, 80 to 100 times per minute. Yet that's not the rate at which your heart is contracting. So anybody have an explanation for that? Your heart, as we're going to find out. Yeah, George?
I was going to say your parasympathetic nervous system acts on it.
Exactly right. So what we're going to discuss a little later is the autonomic nervous system exerts an influence on the heart. So let's make sure we understand the complexity of this picture we're drawing. The SA node is the fundamental timekeeper of the heart. Yet, all of the cells of the heart, to one degree or another, exhibit autocontractility and autorhythmicity. Nice thing, those two words at the same time. That means they will contract on their own at their own individual rhythm. This includes both the pacemaker cells and the contractile cells. Now, layered on top of that inherent complexity, we have the autonomic nervous system intruding, and as we've indicated, as George pointed out here, especially the parasympathetic nervous system is dampening, depressing the rate at which the SA node normally would establish the rhythm of heart contraction. So, yeah, so let's just keep these numbers in mind, and as our discussion continues, maybe we can build upon this. But the SA node typically around 80 to 100 beats per minute. And then, if for whatever reason the SA node is not able to perform its function as the master timekeeper, the AV node, or more specifically the AV junction, we won't get into that, will have a rhythm close to 40 to 60 beats per minute. The AV bundle around 30 to 40. And if we're getting down to the Purkinje fibers and the contractile myocytes, in some cases we're getting close to 15 or 20 beats per minute. So the idea here is we move farther away from the SA node,
Thank you.
the inherent rhythm of contraction decreases. Now, there are a number of factors, especially in your line of work, that will cause these numbers to change, but that's the general rule. Yes.
On our slides, it says the SA node is 40 to 60 beats per minute. Like on this.
Where does it say that?
For your side, it says AV node, ours says SA node. So 40 to 60 beats per minute.
All right.
In the middle on the list, it says, no, to the left.
Your AV node is written as SA for ours.
Ours says.
Oh, that says, yeah, I'm sorry. So just here, yeah, that should be AV node as opposed to SA node. I'm sorry. Yeah, that wouldn't make any sense. And then the AV bundle, what is that? What's the, how else, what other term do we use to describe this? In case there's ambiguity there as well. The bundle of His. So, yeah. And then the bundle branches, remember we said the left conducts a little more rapidly than the right, and the Purkinje fibers are those fibers that extend up from the apex to the wall.
Can you make a distinction where the bundle branch actually ends and the Purkinje never starts?
I don't think that distinction is so important. There's a lot of ruckus in the cardiological literature about the relationship of the AV bundle to the annulus fibrosus and the AV node itself. For example, Guyton and Hall, who writes the fundamental clinical text, will argue that the AV bundle is just an extension of the AV node. But I don't think, for our purposes in here, the anatomical distinctions are so important. Just remember that the AV node is anatomically is just above the annulus fibrosus where the disc set. The AV bundle then, which I fine with me if you want to call it an extension of the AV node, continues through that annulus fibrosus to then below the annulus fibrosus separate into the left and right branch fibers. Now we'll talk about a number of factors that can interrupt normal heart rhythm, and we'll also talk about some of the terminology, bradycardia. It says there, for example, less than 50 beats per minute. Well, you may learn different things in your clinical literature. Conventionally, a 60 to 100 is normal. Anything below 60 is considered bradycardia, but that's going to depend upon your patient, history of the patient, a lot of things. So I'm not too concerned about specific numbers, but this would certainly classify as bradycardia if it's sustained in a normal patient. So normal heart rhythm, again, damage, we're going to talk about blocks a little later, damage to the conductive pathways. If there's some reason, for example, that autonomic innervation is aberrant, we talked about parasympathetic depression of the rhythm. Sometimes the signal it may originate properly in the SA node, but it may not be propagated distally in the way that it should. So there are a number of things. In fact, portions of your heart may just may decide that they want to rule the roost. And in fact, a portion of the atrium or the ventricle may just start to spontaneously contracting on its own. Remember the general rule, whatever region of the heart is sending out the most rapid rate of action potentials, everything else tends to obey. So this type of anomaly is sometimes manifest as ectopic excitation. Some cases, what they'll do in there is just go take a little knife and scrape that area away. Okay, our purpose in here in talking about the EKG is not to become EKG masters. That's what you'll do after you finish Dr. or Professor Sparker's course. We just want to learn a few general concepts and understand the basic terminology and talk a little bit about what the EKG is doing. So we can approach this in a variety of ways. None of my analogies ever seem to be very, very useful. But one analogy might be that we have a car battery. I like the example of a car battery. We have a car battery in our chest. As you know, your heart is sort of lying at an angle. So let's put our car battery. I've got a nice big one out there. I'm going to take that out. I'm going to put it in my chest. And as you know, I've got a positive and negative pole. So you all know what a voltmeter is, right? You put a voltmeter, we get a voltage across. What would the voltage be for a car battery? Yeah, it's usually a little higher than 12, especially if it's new. But that's all right. So we'll say it's 12 volts. So my question for you is, I've got my voltmeter, I've got my red and my black leads, and I put them on the two poles. By the way, how do I know to put them right here? Because it's a big car battery. I just got through putting it in the chest. I kind of know where the positive and negative poles are. So I get 12 volts here right when I put the leads right on the electrodes of the battery. What would happen if I reverse the leads? Would I get the same voltage? What am I going to see then? All right, I'm going to get a negative. All right, so in an EKG, make sure you understand that if the deflection is upward, that suggests one polarity. We say positive. If the deflection is in the opposite direction, that's the opposite polarity. And in part, that's going to be a function of how the electrodes, these little probes I'm using to measure the voltage, are placed in relation to the battery. All right, so I can invert it. You can see what happens there. Let's say I take the positive electrode of my voltmeter and move it closer to the black one. So let's say they're right beside each other. What voltage am I going to get then? Still going to get 12 volts. Start it right here, slide it over. What voltage am I going to get when I put the two electrodes right there beside each other, two leads of my voltmeter? Anybody have a guess? Am I going to get 12 volts? No, not. Probably going to get 0 volts. And if we had a resistance, right, what a resistor is, just a little thing, basically the resistance that is going to vary with distance. So I'm going from 12, and the voltage is going to decrease until eventually it's 0 because I don't have any voltage between these 2 points of the electrode. What's the definition of voltage that we talked about earlier in the year? Difference in charge between 2 points in space. So if I have a small distance, or if there's no difference in charge, I'm not going to get a voltage. So make sure you understand, by way of introduction, when I talk about putting the car battery on the chest, that the signal that is read, both the polarity, the direction, and the magnitude of the signal. By magnitude, I mean how high it is or how low it is relative to the reference point of 0. That's going to depend upon the relative position, the relative placement of what's measuring the voltage. It's going to depend upon how far the electrode is from the battery. All right, so the farther away the electrode, should the voltage go up or down? As I move, here's my battery again, and I'm going to move my electrode way down here, as opposed to putting it right on top of it. Would you expect the measured voltage to increase or decrease? It's going to decrease. So my point here, as we think about the heart being a battery, generating a voltage in an oscillatory fashion, it's much more complicated. Moreover, what the heart is doing is actually changing its position in the chest as it contracts. But the polarity and magnitude then will be determined by the relative physical placement of the electrodes. Now we need to talk about what we mean by electrodes and leads, so let's turn to that. But is that clear? The general idea. All right, in the standard, we're just going to talk about EKG in very general terms. There are various types of EKGs, 12 lead. In fact, some of the emergency vehicles just have a smaller number of leads. But conventionally, there are three bipolar leads. Now, the lead provides a voltage. A lead, technically, to be perfectly correct here, and I know in the clinical literature this distinction will not always be observed, but this is basic science in here, so we're going to try to be technically correct to the extent possible. So a lead, an EKG lead, yields a voltage. What's a voltage again? Difference in charge between at least 2 points. So that means a lead, in order to generate or provide a voltage, must have 2 attached electrodes. Is that clear? Because I'm not going to get a difference unless I have at least two little probes or electrodes. So in the bipolar leads on an EKG, the difference in the voltage is going to be the difference between the right arm and the left arm. Number 2 would be the right arm and the left leg. Number 3 would be in the left leg and the left arm, if you look at our illustration here. So you can see lead 1, 2, and 3, and I'm not so interested in you memorizing what leads 1, 2, and 3 are, but what I want you to notice, and by the way, the electrodes, as you see here, and you can see that in this individual, there's an electrode on the arm, an electrode on each wrist. It can be put on the shoulders, it can be put on the wrist, it can be put on the thighs or the leg, and so on. But with these first set of leads that we're talking about, bipolar leads, we're talking about a simple voltage between 2 different anatomical locations. And those locations are generally, as you see in here, there's something called Einthoven's triangle. Now, by the way, as you look at the illustration there, I can see electrodes placed on the wrist or the arms and on the left leg. Are there electrodes placed on the right leg? So Bob says yes. So why don't they figure into the EKG measurement? All right. So yeah, go ahead.
Aren't those the grounding leads to keep it all in perspective?
All right. Excellent. Both Bob and Abby gave me the answer I was looking for. Now, having done that, you have now assumed the responsibility of explaining to the remainder of the class what a ground is. Go ahead.
I remember correctly, isn't it just a flat line to make sure there's like no complications
Well,
between how you have it, how the triangle is set up?
all right, I think that's true, but let's again, we want to make sure everybody sort of has a very simple and basic understanding before we leave the course. So remember I said that we have a car battery in the chest, that the amplitude of the EKG is going to be dependent upon where you put those electrodes, the distance between the electrodes, the distance between the heart and the placement of the electrode on the body. All right, my question for you is let's say I set the EKG up, and in my bipolar lead number 1, my Einthoven's triangle, I get a measurement at the QRS of, I will just make up a silly number, 25 millivolts. That's not realistic, but let's just make it 25 millivolts. I did that today. I come back tomorrow and it's 18 millivolts. Put it on somebody, it must be wrong. So I put it on Abby and I make the same measurement and I get 4 millivolts. All right. So one way to standardize this, or normal, I guess the better term is normalize this, is to use a reference potential. Look at all the receptacles here. They have 3 instead of 2 little, the older they only had 2, now they have 3. So one analogy, again, my stupid analogies, how high are we now? I'm not talking about your pharmacological, neurochemical state. How high are we right now? How high are we? So you're telling a 5th grader, you want to tell them exactly where we are in space. What do you tell them? All right, so Evan says that we're on the 3rd floor, and you said above sea level. Well, what's a floor? Are all floors the same distance on every building? I'm old. I can remember the buildings that have these giant ceilings. Yeah, these are higher than normal. So that's pretty good, but I have to have a common understanding. What is our general understanding of how do we generally measure height? What's our reference point? I think you said
Sea level.
Yeah, sea level, and we could do that in some universally established unit of distance. So that's what we would do. So all I'm saying here is that the reference potential is analogous to establishing a standard of measure. It's a reference in all individuals. So any voltage that I measure at the arms or at the leg are going to be relative to the ground, the neutral, the sea level that is established by the other leg, usually the right leg. All right, so the other complexity, and hopefully Abby and Bob will help us with this too, are the unipolar leads. Now we have augmented leads and bipolar leads that describe the limbs. So let's make sure we understand this. We talked about what a bipolar lead yields a voltage between 2 physical locations. And right now we're only talking about the limbs. We're talking about the arms and the legs. We talked about how the right leg is used, for example. In the measurements over here on the right, these are called augmented or unipolar because they're not the simple voltage difference between 2 electrodes. These are the difference in voltage between, let's say, the right arm, and I'm going to just sort of make this up, the average of the other 2 electrodes. All right. So not the simple, I'm getting an average. It's called Wilson's something or another. Getting the average of those 2, and then my voltage will simply be between, in the case of the augmented voltage right, between the right arm and again, let's simplify and say the average of the other 2. That's what differentiates a unipolar lead. So this is a little more complicated, and of course the EKG, the computer is going to do all this for you. And defined here is the voltage from the 1 electron. I just fudged it out here and said union of the other 2, but I think the average is all right. So that's the distinction between a bipolar, which implies 2, and a unipolar, which implies more. Now there are also precordial leads. Precordial leads are the 6 leads that go across the chest. Those 2 are unipolar. By that we mean that we're taking the sum or the average of the others and then then comparing that to the signal generated by the other electrode. Now, the advantage of doing things this way, by looking at things from a collective perspective, looking at a combination of leads with each measurement, is that the heart can be, the electrical activity of the heart, the electrical activity of the heart can be more or less understood from different perspectives, different physical locations. If we had a symphony playing here, for example, and you're outside, you could take your ears or your microphone and go around the room and hear different things. Different physical locations at the perimeter of the symphony will yield different sounds. You might hear more violins in one, you might hear more drums in another. And that's the idea behind this arrangement, the precordial leads and the bipolar leads and the augmented leads. In fact, you can sort of see the traditional terminology over here, and you don't have to remember this. I just want you to understand that the function of augmentation in the arrangement of leads and these precordial leads allows the heart more or less to be viewed from the front, from below, from sort of at the septal level, that septum, the atrioventricular septum, and then from the side. Typical EKG would look something like this. We'll come back to this. You can sort of see here are your bipolar leads, 1, 2, and 3. You kind of see them there. These are your augmented limb leads right here, AVR, AVL, AVF. And then what would these be over here? V3, V5. Those would be the precordial. Good. So you see how it's arranged in general. There's going to be your limb leads, your augmented limb leads, and then your precordial over here. And once again, I'm not going to ask that you memorize the perspectives here, but you can see in very general terms what kind of information this yields. This yields, by doing it this way, an appreciation or understanding of the electrical activity of the heart in more or less virtual electrical angles, electrical perspectives, and to an experienced technician or cardiologist, that can be very, very important. Usually the bottom row here is just lead 2 and is used as a standard of comparison. So are there any questions then about the difference between an electrode and a lead, and the difference between a bipolar lead and a unipolar lead? And you can see the approximate placement of these precordial electrodes here. If you look at the illustration here, now we're looking at an actual graph of an EKG or an EKG display here. And you can see we have several important components. We have a P wave, a Q, R, S, and T. The P wave, more or less, and you can look at the figure below. This, of course, is the heart, and you can see these large arrows. So as you look at the illustration here, which is approximately correct, what is suggested by the P wave there? What are they pointing out generates the P wave? What is this? The SA node. It's not really the SA node. It's the electric. It's the contraction. It's the myocardial contraction associated with or resulting from the SA node. And then you can see the QRS is more or less, at least initially, the Q there is associated with the initiation of the signal at the AV node. And then collectively, that QRS, see this giant sort of arrow here? That's associated with the initiation of ventricular depolarization and contraction. Be careful here. That's the initiation, because remember in our contractile myocyte, and we'll look at a better illustration of this just in a moment, the contractile myocyte, depolarization occurred. It was very, very rapid, and then repolarization was sustained. And hopefully by now you remember why repolarization, why that plateau phase occurred. But that's going to correspond to this interval in here, is that plateau phase of the contractile myocyte. And then T, they don't show us very well, but that tends to correspond to ventricular repolarization. In the old days, they would actually use graph paper like this it had, as the paper went under the little moving arm, it moved at a certain rate. And you could adjust the rate so that one of these little blocks represented a unit of time. And so doing that, you get some idea of the time involved, for example, between the initiation of the P wave and the initiation of the Q wave and so on. By the way, you'll notice in this illustration there are intervals and segments. Interval, you can correct, the interval is from wave to wave. A segment is a wave and a corresponding segment, is that correct? So an interval, right, but doesn't an interval always include a segment, or not? Yeah. So it would include at least one wave and a segment. So that's not terribly important. Let's look over here to the right, and we've seen this before. So at the top, we see the EKG trace. And at the bottom, what is that? Yeah, that's the action potential of the contractile myocyte. So our QRS then, this QRS more or less corresponds approximately to the depolarization component. And then from the QRS to the T wave there, you can see more or less coincident or concurrent with that plateau phase, the delay in the contractile myocyte repolarization. So here you have a rather busy diagram of some of the segments in the intervals. Let's just talk about a few of these, and then by the way, the ones in the boxes here are the ones I want you to know. You should know these. But more importantly, I want you to know what they correspond to. So for example, look up there at the RR interval. RR interval. Somebody explain to me what that means. Yeah, go ahead.
That's fine.
Go, Josh. It's the time between one R wave to the next R wave.
All right, so what could you use that? How could you use that?
Regularity.
Okay, good. Now, boy, that's a good term. I've never heard it said quite that way, George. He said regularity. Because I normally think of, I need the fiber. Go ahead.
Count those peaks on your, on your sheet and figure out what the,
Here's where the
heart
word.
rate is.
Okay, you said heart rate and the other word was regularity. Now, do we have a bit of a difference there? Is there a difference between, for example, rate and rhythmicity? So what is the distinction there? And how would this be affected by that? So for example, I say your heart rate is let's make it very simple. Your heart rate is 60 beats per minute. So that means that you would assume what? That go ahead,
Well, I was going to say, if you're counting those beats, if you're counting every one of those intervals, you have a...
all right, but you made the assumption you're going to count every one. In what information can you actually get from just one RR interval?
Oh, okay. From just one,
Why do you say that? Why do you say you have no idea? Because
Well, I was just saying, if you're trying to figure out beats per minute, you need to have more than just one. You've got to know how many are on your strip or whatever, your 6-second strip, and figure out how many are on that, multiply that by 10, and there's beats per minute.
okay, you're good. That's good. And so just to make sure we all understand, what's the problem with counting heart rate or estimating heart rate based upon only one RR interval?
If you assume the rate is always the same, that would mean it keeps consistently the same rhythm. That you could have so many beats per minute, but one could be short and one could be long.
All right, is that clear? Everybody understand the distinction here? We can make a rough estimate of the heart rate. So let's say there were exactly a second between each of these. What would the heart rate be? What would we estimate or assume it to be? Yeah. All right, by the way, if the RR is shorter than 1 second, is the heart rate greater than or less than 60? All right, good. So students have actually fallen for that one on tests, so make sure you know the relationship between the length and the heart rate. But you're exactly right, and the implication would be if we estimated heart rate looking at only one RR interval, is that the, the peaks, the waves would be always consistent. And that's the real distinction between rate and rhythmicity. As Kelsey pointed out, would you expect in a normal healthy patient for the distance between the R and the next R always to be uniform? If it's perfectly consistent, that's almost an indication of pathology. Yeah. Because right now, your heart rate is changing in order to speak. It's changing when you stand up and sit. It's changing as you change the rate of your breathing and so on. And that would be expected. As you lose that ability to vary the heart rate with ambient circumstances, then there's a greater risk of pathology. All right, so I just wanted you to think about this distinction between rate and rhythm. Yes?
Can you please repeat what you just said about
Oh, about what?
students sometimes miss?
Oh, I just wanted you to understand that as we shorten the distance or the time between the R and the R, that would, all else being equal, imply that the heart rate is increasing above 60. And that if I lengthen it, what does that mean? Right, the heart rate is decreasing. And as I say, be aware of these. We'll talk more about, I have a little diagram coming up a little later, but notice the PR interval. It roughly is about what, I always try to make these into one number, but let's say less than 0.2 seconds. That's kind of broad. And that corresponds to what? Why is that? What does that correspond to in terms of the contractiles, or actually in terms of what's happening in the heart? Yeah.
Isn't it the depolarization of the atrium and then the repolarization of the atrium?
Well, that's true. But what's responsible for this distance more than anything else?
The delay in the AV.
Yeah, the delay in the AV. Remember we said it's about a tenth of a second. That may or may not be true. But when you add that to the wave, that's why I was talking about the interval being a wave and a segment. But when you add them up, then what my point is that this is largely determined by that delay introduced at the AV node, and then the QRS should be relatively quick, in less than a tenth of a second there. And then the QT interval, we already talked about this. This is going to be determined, again, in very general terms, primarily by what process. Go back to this, by the way, QT, we're going from here. You're exactly right. Let me go back to this, which is primarily determined by what? So we're going from here to here. As you look down here, what's primarily? The plateau phase. Yeah. So that the plateau, that calcium current is going to be very determinative of that. All right, let's take a break and we'll